Great. So hello everyone, my name is Andre, and after we've heard a lot of trendy GNN and GPU talks, you can relax now a bit. It's a bit more traditional tracking I'm going to talk about, particularly the CPU tracking sequence that we will run in run 3 of LHCb. But first, Isaac already showed you the detector. I only want to highlight again the tracking stations that are, of course, important for the reconstruction sequence. And the charge track reconstruction happens here at the vertex locator. So this is a pixel detector around the interaction point that essentially reconstructs straight lines. Then in front of the magnet, there is the upstream tracker. Also, Isaac mentioned it. This will not be there in the beginning of run 3, so I'm not really going to talk about this. But more importantly, of course, after the magnet, there is the sci-fi tracker. These are scintillating fibers, and it's the big tracking station after the magnet. And then behind there's the path identification, but since I'm going to talk about reconstruction, this is not part of the talk. So this is a simplified view of the trigger strategy we have for run 3. We start, of course, with bunch crossings, and maybe you know that the LHC has, in principle, bunch crossing frequency of 40 megahertz, but relevant for the trigger are only 30 megahertz of this, because these are the ones that are actually non-empty, so where you can actually trigger on something. These 30 megahertz are fed into LHC1, which does a partial reconstruction, reduces the rate of events to roughly 1 megahertz, writes them to a buffer, some alignment, calibration is happening, and then after this 1 megahertz is further processed by the LHCb2, the second high-level trigger stage, which does a full event reconstruction. So this is all online. This all runs in the trigger. There is no hardware-based triggering whatsoever. It's all software-based, and the full reconstruction also features selections that can then be written to storage and further analyzed. You've already heard something about the first trigger stage. It was the first talk by Tom, and there's also a paper if you're interested, and more detailed tracking related stuff for LHCb1. There will be a talk tomorrow by Alessandro. I will be talking about LHCb2, which is fully running on CPUs, so kind of traditional, and it does the full offline quality event reconstruction. This means, well, track reconstruction, of course, this is what this talk will be about. We have a Kalman filter running that estimates the track parameters. There's particle identification, I should say charge particle identification, but we also do neutrals reconstruction in LHCb2. And in the end, you can also select on interesting decays, as this is the job of the trigger, right? More information on general aspects of this you can see later today in Zefter's talk. And if you're interested in this step between LHCb1 and LHCb2 and the alignment and the calibration that's happening, there's also a talk by Florian tomorrow. Whoops. So you've seen a similar picture in Isaac's talk. I would just want to repeat what kind of tracks you can reconstruct in LHCb. So we have a velo track, which is basically a straight line coming from the vertex. We've already heard about the Isaac's trashers, which are these T tracks here. But most analysts are actually interested in these long tracks because they traverse the whole detector, go through the magnet, and with hits in most tracking stations, you get the best momentum estimate out, which is what most analysts actually want. And this is also what I'm going to talk about. So the way we get to these long tracks is depicted here in this flowchart. We start off with velo tracking. So we produce these straight lines coming from the vertex locator. And in parallel, there's the hybrid seeding running that produces these T tracks here. And then you can do a matching between these two. So you run a neural network that just combines the velo tracks with these T tracks, and then you have a combination that gives a long track. So in the past, there's always been two algorithms that produce these long tracks. One is this matching, and the other one is the forward tracking, which is the algorithm I mainly work on. So there's kind of a redundancy in production of these long tracks. And in run 2, both algorithms essentially did almost the same work. So they looked for the same tracks, but because we are constrained to run this now in the trigger, we got rid of this redundancy for speed. So what's happening now is that after the matching found long tracks, the forward tracking looks at the ones that didn't have a match in the sci-fi stations and tries to find hits in the sci-fi station to combine them to long tracks. So how does that work? The forward tracking finds a forward extension in these sci-fi layers. So you take the velo track and you want to find a set of 10 to 12 sci-fi hits that extend this velo track. And these sci-fi hits are on slightly curved lines in the sci-fi tracker because there's a fringe field of the magnet. This is what Isaac is exploiting to measure the momentum. But of course, if we have the velo track in the beginning, the momentum estimate, if we have these hits, then after the magnet, it's much, much better. This is, of course, something we also want to estimate with this algorithm. And because that is traditional, the underlying pattern recognition is something very similar to a half transform. But first, because we want to be fast, we don't want to just look at all the hits for every velo track. We can be smart about it because most of the tracks that have a momentum below 1.5 GeV get wiped out by the magnet anyway. We can define this as the minimal momentum that we want to reconstruct. So we can open a search window that depends on the state of the straight line that comes from the vertex. So this state is essentially just the position x, y, the slopes, and, well, in principle, the momentum that we don't know at this point. So we just assume the minimal momentum that we want to reconstruct. And then we get boundaries in the detector, and we simply look at all the hits that are within this window. As you can imagine, 1.5 GeV is not a lot, so these windows tend to be fairly large. So then the motion through the magnetic field is kind of complicated or computing intensive. So what we do is we simplify the trajectory of a particle through the magnetic field, and we view the magnetic field like a lens. So if you think about basic optics with rays, then you would have this layer here, which represents the layer of the lens. And then you do straight lines, you get a kick, and like the light rays, particle gets a kick and is bent. So we can simplify the trajectory by using this magnet kick position and this slope difference here. And of course, that's a simplification. So there are small errors that we introduce. And particularly in the first station of the sci-fi, we have to correct for these because of the fringe fields that are still present there. The whole goal of this simplified trajectory is then to project all the hits that are present here in these stations within the search window to a reference plane. And using this simplified track model, this can be done quite fast. And then if you project these hits, then you can do something like this is something like a half transform. So what you would like to do then is to fill these hits that you projected onto this reference plane here into a histogram, and then you can count layers that you hit. So I said before, you want to have something like 10 to 12 sci-fi hits. So this is essentially what you are then looking for here in this histogram. And the nice thing about this half-like transform is that it's rather robust. Of course, you have a lot of hits that has nothing to do with the track you're looking at. But these will just look like noise in this histogram. While ideally the hits that actually came from the track you're looking at, so the extension you're looking for, will cluster together in this histogram, which gives you quite a good signature that you can quickly find. And the easiest way to find this is just to scan this histogram and select the bins that are above a certain threshold, which in the end become the candidate sets for this track. So to summarize a bit what I've just told you, so we have this hit search window, then we have a simplified track trajectory. We do something like a half transform to find these sets of hits. And if we have this set of hits, then we do some post-processing. We clean this set up. We have to fit a polynomial to it to extract some track parameters. And from these track parameters, we can, in the end, make an estimate for the momentum and the charge. So I said we have to be fast because it's running into trigger. And typically, when optimizing these reconstruction algorithms, there's a trade-off between efficiency, fake rate, and the event throughput of these algorithms. So you can always sacrifice some efficiency to increase the event throughput, or you can accept more fake tracks to improve your efficiency. But of course, the best way is to just keep it as it is and just make it faster. And the way to go here is using the modern CPU capabilities, namely single instruction, multiple data, or short SIMD, with the structure of arrays. You've heard it already in other talks before. I'm going to quickly explain it anyway. So the idea is, instead of the natural object-oriented layout of a hit, for example, which has maybe positions, a weight, or whatsoever, you store them sequentially in memory, like shown here. So of all hits, all X positions would be stored in one long array. And the same for Y positions or whatever your consists of. This has the advantage that we can use these SIMD instructions of modern CPUs to process multiple of these data points at once. So shown here in this figure, you would process 4 X positions with a single instruction at once. So this kind of data parallelism is very nice to speed up basic computations. And what you get for free essentially is better cache locality of these data structures, which is also very nice for modern CPUs. So how does this apply here to the forward tracking? All these hits and these number of layers in this histogram, so the hits here in the layers of the tracker, are stored in this ZOA layout, so we can directly apply the SIMD instructions. And particularly, we would like to, in parallel, project multiples of these hits. And also the threshold scan here in this histogram can be done for multiple bins at once with these SIMD instructions. And for example, what we are going to use is AVX2. And this means you can process 8 single precision floating points or integer numbers in parallel. And with these simple modifications, the throughput of this algorithm could be increased by 60%. So how does that look in the bigger picture? What you see here is the pie chart of the HLT2 reconstruction sequence of LHCb. And the forward tracking is located, here's the gray part. So you can see it's not a dominating part of the sequence. What is dominating is track fit and particle identification, actually. So these improvements led to this algorithm being not a bottleneck in our sequence. Okay, so of course, tracking algorithms should be efficient, and this is also the case for the forward tracking. Since we are mostly interested in B-mesons, we look here at the efficiency of long tracks from B-mesons, and you can see that for hadrons, meaning not electrons or muons, these the efficiency is way above 90%. For electrons, it's a bit lower because electrons are hard in tracking. They scatter, they radiate, so there's some going on there. For completeness, also the fake track fraction here, this is typically for higher momentum below 10%. At low momentum is of course higher. So to summarize, the forward tracking I present to you, you construct long tracks, which are the best physics tracks at LHCb. The pattern recognition is done via something like a half transform, and the event throughput of this algorithm could be increased by 60% via using of vectorization of CPUs, and the reconstruction efficiency is above 90% for tracks from data sets. Thanks.
Thank you, Andre. Same procedure. Let me check Zoom quickly if you have a question there. If not, in the room. Okay.
So the motivation for using the Hopf transform is the momentum resolution from the Bellow track is not good enough to find the hits inside the sci-fi tracker. So you want to sweep the or possible momentum combinations to find the best track fit.
I don't understand the question. You mean if the half transform is good enough to?
No, I can rephrase it for.
Yeah.
Is the reason you choose the half transform for the track finding that the initial, I think the initial direction from your track before is not good enough to do a track following. Yeah, as you've shown, you have a initial direct. Can you go to this slide? I think. Okay.
Yeah,
something like this.
Yeah, if your momentum resolution from the Bellow track is good enough, then you can.
We have no momentum information here.
There's no more information.
There's no information. These Vedo tracks are straight lines. There is basically no magnetic field at the vertex locator in the beginning.
Okay, I see.
So you start. Of course, if you had a momentum information, there's much better optimizations you can do, and the whole thing would be much faster.
Sorry, since we're on this one, isn't that incorrect? What you're drawing there? Aren't you doing the kick plane at that stage as well? Or is this just this analytic? Is the analytic transform under the assumption of these opening angles giving the track momentum?
This is only for showing how in principle this works. I mean, the projection itself is exactly what is shown here. So you use this magnetic kick plane and the slope difference to correct a bit here for these slight differences for this simplified, and then you just do a straight projection onto the.
That was my question. So 8 is an illustration. Slide 8.
Yes. Yeah.
Okay. Marcus.
Yeah, along the same questions. I mean, would in principle refit these tracks at the end using a proper field integration?
Yes.
Or are you just going with these? No.
The point of this pattern recognition is only to quickly find the set of hits afterwards. So you have also an initial momentum estimate, right? From the slope difference, you can estimate the momentum. But afterwards, the Kalman filter is run to fit the track parameters properly. Exactly. Yeah.
Could you elaborate a bit more about the electrons? Do you have a dedicated algorithm for the electrons, or?
No, it's the same algorithm for the electrons as for the other particles.
But this kind of simplification, like the optical length, does it need to be true for the electrons?
I think the optical length is actually not the. It's not the biggest problem for the electrons, right? The electrons radiate and they might start bending a bit more, so you have more deviations. But I think the main problem is actually the scattering, where you tend to not find as many hits for the electrons as for the other particles, and then you end up with worse quality tracks that might just get removed because they look like ghosts, and this is why you get slightly less efficiency. But yeah, you're right. I mean, in principle, this thing performs less good for electrons because of the radiation. Yeah. But you cannot know which one is an electron, right, beforehand. So.
Very good. Then once more, Andre, thank you.